Today we will be discussing Ohm's law. Once again, if there's anything you miss in the notes or would like to rewatch for any reason, this video will be posted on YouTube and Edmodo. Ohm's law says the voltage, which we know is the potential difference, or EMF, is directly related to the current when the resistance is constant. Remember, directly related means as one gets bigger, the other gets bigger. So, this sentence can be reworded to say, as the voltage gets bigger, the current gets bigger if the resistance stays the same. If we were to write that in an equation, we would use delta V for potential difference is proportional to current. R is going to be our constant of proportionality, which is just the factor by how much one gets bigger compared to the other. In some cases, our factor can be 1. We can have a resistor of 1 ohm. That would mean that as voltage gets bigger, current gets bigger at the same rate. If our resistance is not 1, they won't change at the same rate, but as one gets bigger, the other will get bigger as well. When we add in the resistance to our proportionality, we get that potential difference is equal to current times resistance. We can also say that the electromotive force is equal to current times resistance. If we were to graph voltage versus current, voltage on the y-axis and current on the x-axis, we would get a linear slope. The slope of this line would be equal to the resistance of whatever our electricity is traveling through. Let's focus a little bit more on the term resistance. Resistance is defined as the restriction of electron flow. It is due to interactions that occur at the atomic scale. For example, as electrons move through a conductor, they are attracted to the protons on the nucleus of the conductor itself. This attraction doesn't stop the electrons, it just slows them down a bit and causes the system to waste energy. The unit for the resistance is the ohm. The symbol we're going to use to represent ohm is a Greek letter omega. It looks like a horseshoe. We can think of resistance kind of like running through a line giving people high fives. We can run very, very, very fast if we're not worried about giving each other high fives. But as we extend our arms and try and high five everybody, that slows us down because we're adding additional force. In the general part of an electric circuit, which is the wire, there's very little resistance. But if we look at something such as a light bulb, we have a lot of resistance. And this causes that part of the wire to get hot and produce heat and light. The next thing we're going to look at is electrical power. We have already learned that power is the rate at which work is done. We can also say that as the rate at which energy is transferred. Circuits that are a prime example of this, as batteries only last for a certain amount of time, and we get charged an energy bill each month based on the amount of power we used over the course of a month. Let's track the electrical power. The electrical power starts at the power plant and goes to a transformation substation. From there, it goes through high voltage transmission lines. The high voltage transmission lines feed into a power substation. At the substation, we have a transformer, and what the transformer does is it lowers the voltage of the electricity, making it a little bit safer to be around. Because if we had a high voltage coming into our house, many of our appliances wouldn't work. After the power station, it goes through some more lines, and just before it enters your house, it goes through one last transformer to get the current down to an acceptable size for our house. It is interesting to see how certain electrical variables can be used to get power. Let's start by using voltage and current in the first example. We know that voltage is measured in joules per coulomb. We know that current is measured in coulombs per second. If we take and multiply voltage times current, we get joules per coulomb times coulombs per second. Since we have coulombs on top and on bottom, they would cancel out, leaving us with joules per second, which we know is equal to a watt. And we've learned in the past that a watt is how we measure power. So therefore, we can say that power is equal to voltage times current. We can repeat that previous process using different versions of Ohm's law. We can come up with several different useful equations that involve power, voltage, current, and resistance. You will not need to memorize all of these equations, but please take and draw a large star next to this slide so that you can easily find this list of equations, because they will become very helpful as we try to solve problems. Before we begin the sample problems, please make the following change. For sample problem 1, it currently says find the resistance through a 12 ohm resistive circuit when 24 volts is applied. Please change the word resistance to current. So now the question reads, find the current through a 12 ohm resistive circuit when 24 volts is applied. Our given information for this problem says 12 ohms is our resistance, and we have 24 volts for our potential difference. Our unknown is current, so capital I equals a question mark. The equation that we're going to begin with is V equals IR, which means voltage equals current times resistance. Again, that equation is voltage equals current times resistance. Now we need to substitute in our numbers. So we get 24 equals I times 12 ohms for our resistance. In order to get I by itself, we're going to divide both sides by 12. We get our current equals 2 amps. Our next problem says a resistive load of 600 ohms is connected to a 24 volt power supply. Find the current through the resistor. Our given information, 600 ohms. Ohms is always the measure of resistance, so that equals R. And 24 volts is always our unit for voltage or potential difference, so that equals V. Our unknown in this equation, or in this question, is current, so I equals a question mark. And again, our equation, voltage equals current times resistance. V equals IR. This time, let's try the problem by rearranging the equation first and substituting the numbers second. That would mean we are looking for I, so we have V equals IR. To get I by itself, I must divide both sides by R. So that gives me V divided by R equals I. Because this is only a 3-variable equation, we can always use the triangle method as well. V goes on top, R and I go on the bottom. Remember, the middle line is to divide, and the vertical line is to multiply. So now that we have our equation, let's plug in our numbers. We have a voltage of 24 volts and a resistance of 600 ohms. So our equation looks like 24 divided by 600 is equal to the current. When we plug that number into a calculator, we get an answer of 0.04, and because we were finding the current, our unit is amps or amperes. Problem number 3. Find the applied voltage of a telephone circuit that draws 0.017 amperes through a resistance of 15,000 ohms. So, our given information, we have 0.017 amps, which is our current, which is I, and 15,000 ohms, which is our resistance. Our unknown in this case is voltage, so V equals a question mark. The equation that we're going to use is V equals IR. Because this equation is already solved for the variable we're looking for, we don't need to do any rearranging. So we can simply go ahead and substitute. So we get voltage equals 0.017 times 15,000 ohms. When we plug this into a calculator, we get voltage equals 255 volts. Our last sample problem for today says if a blender is plugged into a 110 volt outlet and supplies 2.7 amps of current, what amount of power is used by the blender? Our given information is 110 volts and 2.7 amps. The unknown for this problem is power. The equation that we're going to use is power equals voltage times current. Our equation's already set up to solve for the unknown we're looking for, so now we just simply have to plug in our numbers. So we get power equals 110 volts times 2.7 amps. When we plug those numbers into a calculator, we get power equals 297 watts. That's all for these notes. Remember, if you missed anything, are unclear on something, or just want to watch this again to study for a test, it is posted on YouTube and Edmodo. And if